Coming up on SpaceTime, what could be the biggest revolution in science since general relativity theory? Unlocking the early universe in 3 dimensions. And India's Chandrayaan-3 enters lunar orbit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
It could be the biggest revolution in science since general relativity, but it's not there yet. A new study claims to have confirmed modified Newtonian dynamics, or MOND, which is a variation of science's current understanding of gravity under special circumstances. If correct, the immense implications would be profound for all of astrophysics, for theoretical physics, and of course for cosmology. In its simplest terms, it would completely change science's understanding of the universe. It would also be vindication for theoretical physicist Mordechai Milgram from the Weizmann Institute in Israel, who 40 years ago first calculated his revolutionary theoretical framework, famously known today as modified Newtonian dynamics, or MOND. The authors of the latest research claim their discovery, which has been reported in the Astrophysical Journal, has met the conventional 5 sigma criteria needed for a new scientific discovery. If confirmed, it would resolve the long-standing mystery of dark matter, that invisible substance that makes up over 80% of the mass of the universe, but which interacts only gravitationally with conventional so-called baryonic matter, the stuff that makes up everything we see in the universe, from stars and planets down to dogs, cats, cars, horses, trees and people. Scientists know dark matter's real only because they can see its effect on galaxies, providing the extra mass and hence the extra gravity needed to hold them together as they rotate, preventing them from flinging apart. However, if gravity was just a little bit different under certain conditions, you wouldn't need dark matter. It might not be real after all. This new study is based on data collected by the European Space Agency's Gaia mission, which has been gathering observations on the exact position and movement of billions of stars in our galaxy, including their speed and direction. In other words, their proper motion through space. The study's lead author Kyuhyun Che from the Sejong University in Seoul decided to examine not the rotation of entire galaxies, but the orbital motions of long-period widely separated binary star systems, which he refers to as wide binaries. Galactic disks and wide binaries share some similarities in their orbits, although wide binaries follow highly elongated orbits, while hydrogen gas particles in the galactic disk follow nearly circular orbits. By taking their measurements to the limit of verifiable analysis, Che and colleagues were able to provide what they claim is conclusive evidence of the breakdown of standard gravity in low acceleration situations in binary star systems. Put simply, they discovered a difference in the way gravity was acting which doesn't match the standard Newtonian model. In order to get as much data as possible, he repeated the observations on 26,500 wide binaries within the 650 light-years observed by Gaia, getting the same effect each time. Che's study focused on calculating the gravitational accelerations experienced by binary stars as a function of their separation, or equivalently, the orbital period by a Monte Carlo deprojection of observed sky-projected motions in 3-dimensional space. He found that when 2 stars orbit around each other with accelerations lower than about 1 nanometer per second squared, they start to deviate from the predictions of Newton's universal law of gravitation and Einstein's general relativity theory. In fact, for accelerations lower than about 0.1 nanometers per second squared, the observed acceleration was about 30 to 40% higher than the Newton-Einstein predictions. In a sample of 20,000 wide binaries within a distance of 650 light-years, 2 independent acceleration bins respectively showed deviations of over 5 sigma significance in the same direction. Because the observed acceleration stronger than about 10 nanometers per second squared all agreed with Newtonian Einsteinian predictions from the same analysis, the observed boost in accelerations at lower accelerations is a mystery. Now, what was intriguing about this breakdown of Newtonian Einstein theory at accelerations weaker than about 1 nanometer per second squared is exactly what Mordechai Milgram first suggested in his own theoretical work on modified Newtonian dynamics, or MOND. Moreover, the boost factor of about 1.4 is correctly predicted by a MOND-type Lagrangian theory of gravity known as equal, which was proposed by Milgram and the late physicist Jacob Bekenstein. What is remarkable is that the correct boost factor requires the external field effect from the Milky Way galaxy that's a unique prediction of MOND-type modified gravity. So what the wide binary data shows is not just the breakdown of Newtonian dynamics, but also the manifestation of the external field effect of modified gravity. Unlike galactic rotation curves in which the observed boosted accelerations can, at least in principle, be attributed to dark matter in the Newtonian Einstein standard gravity model, wide binary dynamics can't be affected by it even if it existed. Standard gravity simply breaks down in the weak acceleration limit in accordance with the MOND framework. Now, if it's all verified, the implications of wide binary dynamics will be profound. Just as anomalies in Mercury's orbit observed in the 19th century eventually led to Einstein's general relativity, now anomalies in wide binaries will require a new theory extending general relativity to the low acceleration MOND limit. Despite all the success of Newtonian gravity, Einstein's general relativity is still needed for relativistic gravitational phenomena such as black holes and gravitational waves. Likewise, despite all the successes of general relativity, a new theory beyond this is needed for MOND phenomena in the weak acceleration limit. Now, if confirmed, it would mean that because gravity follows MOND, a large amount of dark matter in galaxies in the universe as a whole are no longer needed. As for the man who came up with the idea in the first place, well, Milgram put it simply. He says it would mean a new revolution in physics was underway. But for such a far-reaching finding, and it is indeed very far-reaching, science requires confirmation by independent analysis, with preferably even better future data. Milgram says if the anomaly is confirmed as a breakdown of Newtonian dynamics, and especially if it indeed agrees with the most straightforward predictions of MOND, it will have enormous implications for astrophysics, for cosmology, and for fundamental physics at large. And I guess if that's the case, I hope you remember where you heard it first. This is SpaceTime. Still to come, unlocking the early universe in 3 dimensions, and India's Chandrayaan-3 spacecraft enters lunar orbit. All that and more still to come on SpaceTime. The Australian National University is continuing to lead a key project studying the formation of some of the first elements to form in the universe following its creation in the Big Bang 13.82 billion years ago. This decade-long project has been looking back into the infancy of the universe, especially at a watershed event that dramatically changed the cosmos as we know it, from a neutral and dark place to one being almost completely ionized and transparent, basically giving us the universe we have today. It's a period known as the Epoch of Reionization, a time when the first structures in the universe were formed. Despite its pivotal role, the Epoch of Reionization is one of the least understood phases in the history of the universe. The project, under the umbrella of Astro 3D, formerly Castro 3D, seeks to answer significant questions about this time in cosmic history, such as where did the energy to ionize the entire universe come from, and was it simply ultraviolet light from the first stars, or were there other forces at play? And exactly when did the veil of the cosmic dark ages rise, and how long did it take? Tracing the distribution of matter from the earliest times of the universe through to the present day will help astronomers build a three-dimensional picture of the formation and evolution of the universe as we see it today. Astronomers need to know how the structures of the universe, the cosmic web as we see it now, grew out of matter, forming the building blocks of the galaxies, like our own Milky Way. And also, what forces shaped the accumulation and motion of matter in the universe across space and time. To achieve these goals, scientists, including Professor Lisa Cooley, are developing a new generation of instruments to view the sky in more exquisite three-dimensional observations than ever before. The work's being funded by the Australian Research Council's Centre of Excellence for All-Sky Astrophysics in 3 dimensions. It's helping to unlock secrets of the early universe and study the development of elements that make up the periodic table. Hewley says the project's investigating nothing less than how the universe formed its first matter in the dark moments after the Big Bang, how the first stars and galaxies formed and evolved into the galaxies we see today, galaxies like our Milky Way, and how stars created the chemical elements that bathe the universe as we see it now. The research is being conducted by a team of around 200 scientists and engineers from around the world. Part of the project involves the development of new high-tech instruments. These are going to be crucial not just for this project, but also for the next generation of giant optical and radio telescopes, such as the Giant Magellan Telescope and Square Kilometre Array. Hewley says by using the newly developed three-dimensional technology on current optical and radio telescopes, scientists will be able to build a picture of how galaxies formed and evolved across cosmic time. The technology is helping scientists build three-dimensional models which are pinpointing which materials formed in the early universe and map where those elements and stars were born, and also how they evolved into the universe that we live in today.
So we're aiming to use Australia's biggest radio and optical telescopes combined with supercomputers to understand how the matter and the chemical elements in the universe formed and evolved across cosmic time.
The way we currently see this is that the Big Bang itself created, when the universe cooled down enough from a quark-gluon plasma, created the first elements of hydrogen and helium and maybe a bit of lithium and beryllium too.
That's
and
right.
After that, the stars sort of took over that process.
That's right. And so this centre's aiming at these other elements, in particular the carbon and the nitrogen and the oxygen that are responsible for life on Earth.
And we think these are made either stars during their lifetimes, especially big stars. The population 3 stars, for example, would have been huge. They would have made huge amounts of these elements. And the other elements, the heavier elements, were made when these stars went supernova.
That's correct. So there's multiple stars that we need to look at, and we have detailed simulations of entire stellar populations where we have a big theory program in the Centre of Excellence where we're generating whole populations of stars and then joining them together to create simulations of galaxies.
Are we looking at watching them evolve and see how they change with age through time?
Yeah, that's right. So in the simulations we can do that, and then with observations what we're going to be doing is we're going to be using the Milky Way to look at stars that formed at different times. We're going to be looking for the oldest stars in the Milky Way, which could be the first stars that formed in the universe, and also we're going to be then looking at the first galaxies that formed in the universe. We're going to be doing that directly with the James Webb Space Telescope, and after that we'll be looking at galaxies at all different distances from us, and with that, we can actually look back in time many billions of years. We've used the Hubble Space Telescope to look at very distant galaxies, and those galaxies look very different to the galaxies that we see today. So the distant galaxies in the very early universe were very clumpy and lumpy and very messy looking. They don't look anything like our beautiful spiral Milky Way galaxy or the elliptical smooth galaxies that we have around us. So we're hoping to look back even earlier to look at the building blocks of those galaxies, the smaller clumps of matter and the smaller clumps of star formation in the very early universe to see galaxies when they were actually first forming.
One of the big hopes of James Webb also, and I guess a dream for many astronomers, is to actually see a population 3 star.
Yes, that's right. So that's one of the hopes for this centre as well, is to see a population 3 star, and we're aiming to do it in 2 ways, with the Space Telescope, but also by looking at studies of millions of stars in our Milky Way.
These population 3 stars are very important, these first stars. They're very different from the stars we see today, aren't they?
Oh, they are. They've got a very strange amount of elements in them. They're very pristine. They've got hardly any elements that we have around today in our Milky Way. So, for example, if you're looking at they're looking at the oxygen or the iron in them, they can have very, very little oxygen or iron.
When you have that sort of lack of metallicity, which is what we refer to when we talk about elements other than hydrogen and helium in the periodic table, when you have so little metallicity, that must make the star look very different. It must be a very different type of star to what we have today, in terms physically of size and mass.
We haven't found them quite yet. We've found stars that are very close, but not quite discovered those first stars. The galaxies were very messy, they were clumpy, and some of the galaxies were very, very blue compared to today. They had much more star formation. They had much more star formation happening per given volume than they do in galaxies today.
30 times more than the Milky Way does now back then.
We are discovering galaxies with spiral arms that have already been cleanly formed around 6 or 7 billion years ago, so they must have started forming earlier.
Galaxy clusters, some of them are believed to have been formed very early on too.
Yes, so galaxy clusters seem to have been formed many billions of years ago, maybe 8 or even 10 billion years ago the first clusters would have been forming, and we've been looking at some nearby, what we call nearby galaxy clusters. They're actually about 8 billion years ago. We look back in time, and we're both looking at with understanding the star formation happening within the galaxy clusters, and also we're using them as gravitational lenses. The big galaxy clusters bend the light from background galaxies and magnify it and allow us to see the light from the background galaxies that would be far too faint for us to see with our modern day telescopes. So the galaxy clusters are useful for many different reasons.
Is it fair to think that because the universe was a physically smaller place back then, hadn't spread out as much, hadn't expanded as much, that makes perfect sense that there would have been galaxy clusters so early on?
Yeah, so we think that galaxies were having lots more collisions and were much closer together in the past, and we think that also contributed to the large amount of star formation that we see in the early universe. When galaxies collide together or pass close by each other, there's a lot of gas collisions happening within the galaxy. Their gravitational potentials are disrupted, and there's tidal forces, large tides occurring through the galaxies, and then this causes gas collisions, which then causes star formation to happen in the densest regions of the gas.
Why is reionization important? What does that tell us about, the universe we live in today?
Yeah, reionization is incredibly important because this was the time when the universe changed from being in the dark ages to the lit universe, when the first stars and the first galaxies and the first black holes lit up the universe. And it was basically a watershed event in the history of the universe, and it was the first time ionizing radiation that rips electrons off atoms. It's the first time that was produced in the universe, and our current universe is 99% ionized, and how it got to this state is unknown, and that's one of the goals of this centre, to explain how the universe reached this level of ionization.
That's Professor Lisa Cooley from the Australian National University. And this is SpaceTime. Still to come, India's Chandrayaan-3 spacecraft enters lunar orbit, and later in the science report, a new strain of COVID-19 that's fast becoming one of the most prevalent variants. All that and more still to come on SpaceTime. India's Chandrayaan-3 spacecraft has successfully transitioned from an Earth-centric to a lunar-centric orbit, marking a major milestone in India's ambitious lunar project. The ISRO, or Indian Space Research Organisation spacecraft, is carrying the Moon Mission 3 lander, which is slated to descend to the lunar surface on August the 23rd. Mission managers say the 3,900 kilogram spacecraft is performing nominally. The probe successfully undertaken a series of planned orbital reduction manoeuvres designed to tighten its orbit, and these will continue throughout the coming week. Then the Vikram lander will be deployed to begin its journey down to the lunar surface. The target is the Moon's little explored South Pole region. If successful, India will become the fourth nation to have achieved a soft landing on the Moon, behind the Soviet Union, the United States and China. Once on the ground, Vikram will release the 26-kilogram Program rover. The tiny six-wheeled vehicle will explore the Moon's South Pole region, examining the Moon's surface composition, its thin exosphere, and its tectonic activity. The presence of water at the bottom of craters in permanently shadowed areas of the Moon's South Pole will be of special interest for this mission. We'll keep you informed. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new strain of COVID-19 is fast becoming one of the most prevalent variants of the disease in the United Kingdom and United States, and Australia will most likely be next. America's CDC says the COVID subvariant EG5.1 first showed up in February and quickly began dominating cases, in the process joining the other 7 common variants circulating throughout the community, which are now being monitored by the World Health Organization. Immunity researcher Professor Cassandra Berry from Murdoch University says the EG5.1 variant is descended from the lineage of the Omicron variant of SARS-CoV-2. That suggests that immunity to Omicron will provide a level of protection against the new strain and lower the disease severity. But she says it's still important for people to stay up to date with their vaccination boosters, as the threat of disease from these pandemic viruses is not over. Right now, some 7 million people have been killed by the COVID-19 coronavirus since it was first detected near China's Wuhan Institute of Virology back in September 2019. The World Health Organization estimates the true death toll is likely to be around 18 million, with some 768 million confirmed cases globally, almost 10% of the planet's population. A new report warns that the Great Barrier Reef is likely to face impacts from climate change that could become irreversible around mid-century, regardless of whether global emissions stabilise. That's the latest warning contained in a new study by the Australian Academy of Sciences. The report explores different possible future scenarios for the Great Barrier Reef under different emission levels. A total of 84 multidisciplinary experts joined the roundtable discussions, the first on climate impacts on functions of the Great Barrier Reef, the second on interventions, and the third on the future of the reef. The report makes it clear that climate change remains the primary threat to this global icon and its connected systems. Scientists have discovered the remains of what might well be the largest animal that ever lived. The 39-million-year-old whale fossils, reported in the journal Nature, were uncovered in southern Peru and include 13 vertebrae, 4 ribs and a hip from a basilosauride whale estimated to have been somewhere between 85 and 340 tons in weight. Paleontologists say that at the higher end of this estimated range, the whale, named Perucetus colossus, would have been both longer and heavier than a blue whale, which at 29.9 metres in length and a mass of up to 219 tonnes, is currently believed to be the biggest animal that ever lived. The authors say the buoyancy associated with the increase in bone mass is consistent with a shallow water lifestyle, supporting the idea that basilosaurids were hyper-specialised for coastal environments. If you're trying to become a famous mega rock star, but the talent train's already left the station, what do? Well, you marry a ghost, of course, just before you release your latest album, and make sure as many people know about it as possible. However, as Tim Mendham from Australian Skeptics reports, it's a marriage that never really had a ghost of a chance.
There's a singer in the UK named Brock Hard who supposedly married a ghost a few years ago. To the surprise of her fans, I presume she had some fans, and she married this ghost, an interesting experience.
Brother and mum.
And the sad person down the road. And now she's actually found out that the marriage wasn't as good as it was going to be.
A bit one-sided.
Didn't have a ghost of a chance, right? So she's now getting divorced from the ghost. I really don't know whether the ghost worries about those legal niceties of having a bit of paper saying you're divorced. So she's turned to an exorcist to end her tumultuous marriage after 5 miserable months of being married to the paranormal character. Okay, that was a relationship that worked well or didn't last that long. But she said it was like carrying a huge weight. I didn't think ghosts were heavy anyway, exactly, but never mind. Yeah. Carrying a huge weight around, the responsibility, I suppose, of looking after a ghost.
What responsibility? I mean, ghosts are pretty well self-cleaning. They don't leave a mess around the house normally.
They don't have a lot of clothes to worry about.
Exactly, nothing to wash.
Yeah, that's right.
Bed sheets, maybe.
Yeah. Ooh, we have to patch up those holes where the eyes are.
Yes.
The strange thing is you sort of wonder what this is about. No,
I just don't think she got the spirit of things.
Yes, yeah, thank you. You wonder what is happening. She was, her ghost was named Eduardo with a W, not an E-D-U-A-R-D, but Eduardo, and she was looking forward to starting a new life. I don't think she's going to have a family, but never mind. But why was it happening? Oh, she's a musician, and she's got a new record coming out. Pardon my cynicism, but I would suggest she's trying to get publicity. And she was trying to get publicity the first time, and now when she got married, now she's trying to get publicity because of the divorce. And that's me being terribly cynical. But she's a person, if you go onto the news sites and have a look at the stories about her, she's a person who loves to pose. She's posing in cemeteries, this sort of coy look, heavy on the eye makeup and all that sort of stuff. And
it's all about me.
I think it is all about her, yeah. And I think she's trying to sort of muster up some publicity for her new record coming out just now. I don't know what it sounds like. I haven't heard the record. It might be played backwards. I don't know. It's one of those sort of sad but interesting stories that we get hit with a lot.
It's like watching the Sussexes, isn't it? You know, we want privacy. We want privacy.
Yeah. It's also very much, you wonder, I don't think most people take it that seriously. So I don't think it's going to be the end of the world sort of story if she gets divorced and then remarried again. You know, it's one of those things.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.